Defining the autistic phenotypes is not difficult. Understanding it and bringing real-life data and experiences can bring these autistic phenotypes into power. For today's episode, we will continue autism and sensory processing. We will explore 4 scientific articles related to autism and the sensory processing phenomena. We will spend time on the mesencephalon. We've covered this in previous episodes, the Autism and Eye Movements episode, and part 1 of Autism and Sensory Processing. The mesencephalon is a very unique and dynamic structure of the brainstem, a little area of the brainstem. From embryogenesis, this cell type, one of 4 cell types during embryogenesis, does not evolve into larger, more complex structures. This says magnitudes about its role. The mesencephalon has the superior colliculus. Remember the Autism and Eye Movements episode. And the inferior colliculus. This unique area of the brainstem, its role, it's very machine-like. You cannot shut it off. It will just respond. The role, its very powerful role here, is to bias the living organism to the outside world. It biases our attention to the surroundings. If you think about autism, if you think about even the Kanner and Asperger papers, this is well known. This is well established. It is easy to see in the autistic phenotype. Now just imagine what this means for learning, especially during the critical period and even before the critical period, and so on. We know in autism research, the salience network is abnormal in autistics versus typicals or control groups. It's not disputed. Now with autism, there's always all these XYZ comorbid conditions. There are a few that are more consistent, such as the sensory processing phenomena with autism, the speech and language, and gastrointestinal problems. Those 3 things are mostly common across all autistics. And probably the 4th is the eye contact. So with this sensory processing, let's go into Article 1 from Marco et al., 2011, called Sensory Processing in Autism, a review of neurophysiological findings. This study conducted a comprehensive review using EEGs, electroencephalography, MEGs, magnetoencephalography, and functional MRIs, fMRI. And they explored auditory, tactile, visual, and multisensory processing. Now with senses, it's mostly multisensory. We are integrating multiple senses into one perception or to many perceptions. And this is precisely what the mesencephalon is doing, integrating sensory and biasing attention. So the auditory system, Marco et al. Explored the brainstem and membrane. And they found inconsistent data here. There's no significant differences between autistics and typicals. In children and adolescents with autism, when processing complex stimuli like speech sounds, these inconsistencies suggest a disruption in early auditory pathways, potentially the inferior colliculus, or even earlier, before the stimuli gets to the inferior colliculus. However, with the cortical level, they use an event-related potentials, ERPs. And they cite EEG and MEG studies showing that early auditory cortical responses using N100s or M100s can be delayed or accelerated in autistics. Now, N100s is a tool used for EEGs, and this is a negative going peaks, and it occurs 100 milliseconds after the stimulus. It is recording this time frame. It captures the brain's initial detection and sound processing. So 100 milliseconds after a sound, your brain should register it. Same for the M100. N100 is EEGs, so electrical. M100 is MEGs, so magnetic. The M100 is better at local brain activity, just one brain area or very small brain area, whereas the N100 provides more broad and distal measurements. One study reported a 10 to 20 millisecond delay in N100 latency for just pure tones. Another study found accelerated M100 responses to pitch changes. The delays and acceleration with autism. This suggests that the brain of the autistic phenotype is processing these differently and is trying to compensate something. Something is abnormal in this flow of signals. If you think about the roadmap, we often use these roadmap examples or linear progressions. Point A to point B. What is the best route? The brain of the typical developed person, the living organism, is going to make this as efficient as possible. This is the role of the brain and central nervous system, to conserve and allocate energy, to make it most efficient. Another tool that they use is mismatched negativity, MMN. And this peaks around 150 to 250 milliseconds. And it shows faster latencies in autistics versus controls. Autistics is less than 140 milliseconds, whereas controls 160 milliseconds. And also increased amplitudes, so higher pitch deviations, higher processing. This is at a localized level. It shows that there are disruptions at the localized area, and this implicates downstream processes. So for attention modulation, because this is what we are doing, we are extracting data from the environment and trying to make sense of it. The study explores covert, so internal focus, or overt, external focus. And they find that children with autism exhibit reduced modulation of auditory responses under direct attention task. In other words, they are not paying attention. They are not influenced by things from the environment. It's pretty easy to see this. It's well known. But the purpose of this is kind of to understand by how much and where. Okay, so for the tactile systems, touch. So the peripheral will be involved here and the central nervous system. There's two pathways. There are hypersensitivity could stem from overactive vibration sensitive receptors. Now this is what the receptor is trying to do. It senses vibration, the sensitivity of the vibration. This is what it's measuring. What does that touch? What kind of vibrations are coming through the skin and being processed up through the brainstem to the brain? What does that mean? There's a type of receptor there. I'm not going to enunciate it. But the study shows for autistics, there's a reduced inhibitory modulation. And this is probably due to that EI imbalance, excitation and inhibition. So increased excitability or the altered inhibitory control. The study specifies that when auditory and somatosensory stimuli are presented together, the early electrical potentials, so less than 100 milliseconds, and primary sensory corticals are relatively sparse in autistics, and the amplitudes comparable to the controls. However, this data is inconsistent across the board, which makes sense because the autistic phenotype, there is a large spectrum of sensory processing problems, not only the types for the living organism for that specific autistic phenotype, but at different times. There's a lot of hypo and hyper sensitivity. So Marco et al., the visual system, and it studied early visual processing, specifically things like contrast or motion. They report normal perception of simple visual stimuli, alongside enhanced perception of details, such as faster detection of embedded figures. There are higher reaction times for the autistics versus the control. But there are deficits in complete task, like motion coherence. The accuracy for autistics for motion coherence is much less than controls. Another thing they studied is face processing. So the fusiform gyrus is heavily involved and heavily researched with autism here. It's a little part of the temporal lobe. And the fusiform gyrus detects face perceptions. The study found reduced activation in this area and in the amygdala. Using fMRI studies, they show decreased bold signal versus controls, nearly 1/2 difference. In other words, the controls are twice as better at doing this task. The connectivity issues here with the fusiform gyrus and the amygdala. They used local cortical activity, so there's an increase in gamma band power. Everything we're talking about are releasing oscillations. There's different ranges of oscillations, and I won't say these in order, but they include alpha, theta, beta, and gamma. There's low gamma and high gamma. With autism, there's the impaired long-range connectivity. So there is a reduced coherence between occipital regions, the back of the brain, and the distal frontal area. These are very distal, as far as you can get in the brain. This could explain the hyper-detailed perception and integration challenges. So finally, the multisensory integration, the study of integrating these senses. They looked at neural networks and integrating across modalities. So if there's a flash beep illusion, this is less efficient in autism. They detail that when auditory, for example, 1000 hertz tone and somatosensory, a finger tap, stimuli are paired, early responses, less than 100 milliseconds, in primary sensory corticals remain intact, no problem. But later responses, around 175 milliseconds, are reduced and delayed. This suggests both the magnitude and latency issue. In multisensory integration, these deviations and the sequence of brain activity during sensory collapse. This is what they're labeling it. This is suggesting that downstream there is a problem in integrating and processing these senses, making sense of the environment. Some more detail about the Marco et al. Study, 2011. So some brain architecture as well. They use postmortem studies that these reveal denser organization in the neocortex. So the neocortex, they have columns. And there's a thing called mini columns. And in autism, autistics have narrower mini columns. So roughly 30 to 40 micrometers or microns. So if you would shave a piece of paper in equal halves, the thickness, this is what we're talking about. This is the size. So controls, these mini columns are 50 to 60 micrometers. So it's about 35% smaller. And this could potentially boost local processing, but disrupt long-range communication. And the cerebellum here shows significant neuronal density changes. There's a thing called Purkinje cells, mostly in the cerebellum. Now, Purkinje cells are very underrated. In autism, there's massive data suggesting implications here. The cerebellum as a whole is probably underrated. And these Purkinje cells could have some key information. What they show here is this loss of Purkinje cells could implicate the multisensory integration. So also with Marco et al., the higher order multisensory integration, so speech comprehension and production. Speech perception, they study. Note that in audio-visual speech task with a temporal mismatch, for example, 200 millisecond offset, individuals with autism perform at chance levels, so roughly 50%. However, controls are greater than 80%. This indicates massive deficit in integrating auditory and visual cues. There's a McGurk effect. You can look up the literature on McGurk effect. And autistic participants show reduced fusion rates, nearly 1/2. In other words, the controls are twice as better at this, reflecting less reliance on visual feedback. So things like lip reading and phoneme perception. Now, phoneme perception, this phoneme process, is complicated. It's complicated for autistics. I'm not going to go into it. They also studied the impact of noise in noisy conditions. For example, 5+ decibels, signal to noise ratio. Typically, the developing individual improved comprehension with visual cues. Comprehension and visual cues add 20% accuracy. But for the autistic phenotype, they show a minimal gain, less than 5% when adding in these. So if you use visual cues in a noisy environment, how much does that help by adding in the visual cues? So Article 2, brainstem transcription of speech is disrupted in children with autism spectrum disorder. This is by Nicole Russo et al. This comes from Nina Krause's lab at Northwestern. Nina Krause studies the brainstem region, and they do a very good job of studying this area and the implications of the brainstem problems. They have a lot of work on this, so I just chose one article from them. Nicole Russo is no longer at Northwestern, but she is still continuing work on this area. So this study investigates the brainstem responses to speech in children with autistic phenotype compared to the typical developed. and they focus on how speech sounds are processed in both quiet and noisy environments. This is a very good study here. Remember me talking about in noisy environments, eventually sounds start to blend. Everything starts to sound like an older Beatles track towards the end of the song, where they start experimenting with various sources of sound. Everything's just blended together, making noise. This is the way I feel in noisy environments. So there's a thing, the Auditory Brainstem Response, ABR, and they use a simple speech syllable, da, D-A. And they presented this in both quiet and noisy backgrounds. So the findings of this study, children with autistic phenotype show significant deficits in neural timing, the synchrony, and the frequency of the encoding, phase locking it's called, of speech sounds, despite having normal click-evoked ABRs, auditory brainstem responses. So in noise, the brainstem response for the autistic phenotype were less faithful to the stimulus. And this shows a reduced amplitude and increased latency again, suggesting a greater vulnerability to the background noise. Remember my Beatles comparison. This background noise is coming in. So the study found that correlations between the brainstem response measures and the language abilities indicate that poor neural synchrony in noise was related to lower language scores. The implications here are, the findings suggest that the brainstem-level auditory processing deficits contribute to language impairments in autism, another frequent comorbid problem. Speech and language is very much alive with every autistic phenotype. So this could serve as a clinical tool for assessing the auditory processing issues and the monitoring the effects of this auditory training for autistic phenotypes. Okay, the brainstem auditory pathway. So this demonstrates that the children with autism and these deficits in the neural timing and frequency encoding, despite having the normal responses in simple auditory stimuli, the effects of this noise shows that the background noise disrupts speech processing more significant in autism, indicating of the noise suppression problems, the inability to inhibit the background noise. Or it could say that the signal enhancement in the auditory brainstem is abnormal. These biological implications could be, it indicates that language impairments in autism could partly stem from brainstem level processing deficits. Remember what we said at the beginning of the episode. This brainstem area, the mesencephalon, is going to hold keys to understanding autism. So autism research ought to go to this early developmental finding and this epoch here to understand what is disrupting this in the auditory pathways that affect the so-called bottom-up and top-down sensory processing. So some biological details here of this study. So the neural synchrony, synchronizing the neural networks. And this delay in the neural timing, specifically waves V, A, D, F, were observed. And this indicates how auditory information is processed at the brainstem level. Now to clarify, before we move on any farther, waves VA, DF. So waves VA are more for onset responses, and waves DF are frequency following responses. So for the phase locking, these deficits that encode the fundamental frequency of speech sounds were noted. So think pitch, perception. We've covered this a little bit in this speech and language episode and in earlier episodes even. Things like prosody. This is a big problem here with autism, that so-called monotone voice even. A significant mention here about the phase locking and the autistic phenotype, okay, suggesting that this brainstem of the autistic phenotype, it does not encode speech sounds as effectively compared to controls. And the noise impact, back to the Russo study, the noise impact, responses in the autistic phenotype degraded more in the noisy environments. So this kind of suggests that it's less effective neural mechanisms for noise suppression or signal enhancement. How do living organisms learn to quiet the noise and attend to whatever is being focused on, whatever has our attention, that task at hand? So we've talked about neuroplasticity quite a bit, and we ought to. This very much should be a region of interest for everybody living, autism or not. We change. We change from experience and so forth. We've also talked about afferents and efferents, connections to and from different brain regions. Now, the brainstem here is also plastic. So the study highlights the plasticity of the brainstem, the responses by experience, like linguistic or music training, suggest that the top-down cortical influences might be atypical in autism, and this potentially affects how sensory information is processed. We need to talk about the neuroplasticity and repetitions and so forth, trying to rescue these poor connections, these poor brain regions. This is very much a thing, and it takes a lot of work. If you remember back to the first episode of the podcast, Dr. Catherine Lord, she mentioned how funds and sources are not readily available at these lower level areas that can help the autistic phenotype in day-to-day activity. This is where money and resources need to go. This is what's actually doing the changes for the specific autistic phenotype. Okay, if you're hanging in, we're at Article 3, describing the sensory abnormalities of children and adults with autism. This is by Leekam et al., I believe. Leekam. Leekam et al., 2007. So the objectives and methods used here. The research attempts to describe patterns of sensory abnormalities in the autistic phenotype using DISCO, Diagnostic Interview for Social and Communication Disorders. It's just an autistic form. This study documented that sensory abnormalities across a lifespan, so more of the neuroplasticity across the lifespan of the autistic phenotype, compared to clinical groups, and this is using detailed caregiver interviews for the children. This study has two different experiments. So study 1 compared sensory responses of 33 children with autism with clinical comparison groups. So it studied language impairment, developmental disability, and typical development. So findings from study 1 show that over 90% of children with the autistic phenotype had sensory abnormalities. I'm surprised it's not more than that, but that's significant. And this is predominantly in multiple sensory domains. Of course it is. And the significant differences are visual, smell and taste, and touch compared to the clinical controls. And people with high-functioning autism, the children showed that they had more sensory symptoms than the matched controls. Study 2 examined 200 individuals, N200, with the autistic phenotype across various ages and IQ levels to understand the persistence and change in sensory symptoms. Study 2 finds that sensory abnormalities were 92.5% of the participants and multimodal, persisting across ages and IQ levels. Some of these symptoms varied with age and IQ. For instance, visual symptoms decreased with age, while some proximal sensitivities might increase with awareness. Some main findings of this study include: it confirms that the sensory abnormalities are a core aspect of autism. If you look at the criteria of the DSM, it spends some time on highlighting the hypo and hypersensitivity of this sensory processing. And these could be rooted in the biological mechanisms that we are talking about today that affect sensory processing and the integration, with the implications for understanding the developmental and biological basis of this autistic phenotype across the lifespan. The study attempts to highlight neural connectivity and even some neuromodulator, more accurately, function. So the presence of both hypersensitivity, so overreacting to stimuli, and hyposensitivity, underreacting, points to a dysfunction in sensory modulation, which might involve some of these modulators that we've discussed, such as serotonin and certainly GABA. The neural circuitry, the enhanced local processing might occur at the expense of long-range connections. A lot of these areas or these studies are showing localized versus distal connectivity problems. And lastly, on Article 3, the study kind of highlights the need for the neuroplasticity. There's a lot of interest here. There's a lot of attention that ought to go to these therapeutic interventions. And remember the autism and eye tracking episode, the biomarker. And I say that it's obvious that the earlier the recognition, the better the outcome. It seems simple on the surface. Seems that's easy to understand. You recognize something early, and before the neuroplasticity, before we become who we are more and more. Because remember a goal of the central nervous system and the brain, shifting learning into habits. We build habits. And this is essentially just strengthening of connections. It requires less energy. We just respond. So Article 4. Now we're going through these last articles in less detail, and that's okay. So this article is Tomczyk and Dunn, also from 2007. So this is these 2007s. They're kind of old, but this is called Sensory Processing in Children with and Without Autism, a comparative study using the short sensory profile. The behavioral sensory responses. So while not directly discussing the biology, just briefly, the methods used is the Short Sensory Profile, SSP, which is a questionnaire completed by caregivers to compare sensory processing behaviors in children with autism against typical developed peers. And it focuses on the domains of tactile sensitivity, auditory filtering again, and sensory seeking. The study does not go into biological details like I pretty much prefer and the other studies, but there is a high prevalence of sensory issues. They find 95% of autism have the sensory processing phenomena. So we're always 90% or above with this autism and sensory processing implications. It's possible that this is involved in the neurotransmitter system and the neural pathways that we've discussed before. They don't go into a lot of detail here, but the thing I want to highlight is that 95% again, The main findings of this study that it implies that the sensory processing dysfunction in autism is not just a behavioral manifestation, but a predisposition of our biological development. And this affects multiple sensory domains, and it suggests a need for biological investigation into our sensory modulation mechanisms. And that's what I really want to highlight here, that role of the brainstem, and specifically the superior colliculus and the inferior colliculus of the mesencephalon. If you look at the embryogenesis, things like the neurulation and the neuroepithelial cells, it creates 4 cell types. One of the 4 is a mesencephalon, and it does not evolve into larger, more complex biology and structures during this process of developing the central nervous system, the brain, and spine. If you think about, we use one of the 4 dedicated cell types here, specifically for this small area of the brainstem. This is telling me this is vastly important because Mother Nature has not evolved it to do anything else. Evolution says, stay put. This is all you need to do. And we overlook that. If you're listening to the podcast or listening to the episode, please feel free to leave a review or rating. In podcasting, reviews, ratings, and downloads are huge, and I very much appreciate your feedback. You can contact me on X at RPS47586, and I would love your discussion about autism. I'm always willing and available to discuss autism with you. You can check out the Hop link so you can have links to all of the shows across different platforms of podcasting and my contact information. You can email me info.fromthespectrum@gmail.com. And lastly, check out the YouTube videos. You can have shorts and full-length videos. There are many good shorts on YouTube, I believe. Many great so many wonderful guests of the podcast. These are very incredible individuals. Very thankful for their interaction. I cannot believe I get to discuss autism with them and with you. And thank you for listening to From the Spectrum podcast.